For the last part of Unit 4, I wanted to talk about something called extraction. I'll be talking about how we can extract one variable out of another variable. But before I talk about extraction, first let's review how we can use regression to predict people's scores, because the idea of extraction will build on this concept. So what we've been talking about for this unit is how we can create a regression equation where we predict people's scores on y with an equation that has an intercept and a slope. And we can say that a person's predicted score on y is equal to an intercept plus a slope times their score on x. And we calculate an intercept and a slope that will minimize the sum of the squared error. And to do that, we can use these equations that I have on this page here. So for the slope, our equation is covariance divided by the variance of x. We'll calculate our slope. And for the intercept, we take the mean of y minus the slope times the mean of x will give us an intercept. And in the example we've been using throughout this unit, where we've been using traumatic bunny incidents to predict people's anxiety, we ended up with an equation. When we plugged in this formula, we had a slope of 2, and we had an intercept of 12.5. So the example we've been using, our equation has been 12.5 plus 2x. So if we take someone's score on traumatic bunny incidents and multiply that by 2, add to that 12.5, we get their predicted score on anxiety. And this table here is the same table we've been looking at throughout this unit, where we have a sample of 1, 2, 3, 4, 5, so 8 people. And for these 8 people, we have everyone's score on traumatic bunny incidents and everyone's score on anxiety. And in this slide, I've added to it their predicted scores. And I just plugged in our equation that we calculated earlier, where I take an intercept of 12.5 and a slope of 2. And so, for example, here's Cal, and he had a score of 3 on x. So I'll just put a 3 right here. X is 3. So 3 times our slope of 2, add to that 12.5, our intercept, and I get a predicted score of 18.5 for Cal. And so I put a predicted y hat in this third column for Cal. Or let's see, we've got Gus over here. Gus had a score of 8 on x, so I'll put an 8 right there. That's for the x in our equation. 12.5 plus 2x, 12.5 plus 2 times 8 for Gus gives us a predicted score of 28.8. So we predict, based on our equation, we predict that Gus's anxiety should be at a 28.5, and we predict that Cal's anxiety should be down at an 18.5. That's our prediction based on their scores on X, based on the number of traumatic bunny incidents they had. This is what we predict their anxiety should be. And then recall that we calculate an error for every single person, which is simply the observed anxiety minus the predicted. So for Cal, he actually had a 5. He has a really low anxiety, but we predicted 18.5. And so observed minus predicted is negative 13.5 for Cal. And for Gus, we observed he had a 35 was his anxiety. We predicted only 28.5, and so his error is positive 6.5. Observed minus predicted gives us 6.5 for Gus. And so this table is showing you scores on X, scores on Y, Y hat, predicted scores, and then our errors observed minus predicted for each person. And just to recall, this is the slide I showed you earlier to illustrate what the errors look like. The error is simply the difference between the observed scores of the black dots, and the predicted scores are given by our red line, that slope. And so the difference between the black line and the red line, or the black dot and the red line, is the amount of error that we make. And so here we've got that, this must be Cal right here, who had whose actual anxiety was way down at a 5, even though we predicted, we can see right here, we would have predicted 18.5. His actual anxiety was a 5. So 5 minus 18.5 is 13.5. That's why it says 13.5 down here, because his actual anxiety was 13.5 units below what we predicted. Okay, Now that we have reviewed how we can use regression to predict people's scores, we're ready to talk about extraction. So, what is extraction and why is it important? What we're going to be talking about is a process of extracting one variable out of another variable. And this is something that is actually quite important because, well, there are many situations in research where we want to target and understand and investigate a particular variable, but we have a problem that that variable we want to study overlaps with other stuff. And so if we study that one variable, we don't know, are we studying the variable we want to study, or are we accidentally studying all the other things that overlap with that variable that we want to study? For example, maybe I have a hypothesis that the more often people wash their hands, the less often they'll get sick. So my hypothesis is that hand washing will predict health, or it will correlate with health. But maybe people who wash their hands more frequently are also people who eat more vegetables. And so if I do a study that finds that hand washing predicts health, I don't know, is it because hand washing is actually directly predictive of health, or is it really the vegetable eating that overlaps with hand washing that's predicting the health? Is it the vegetable eating or the hand washing or both that are predicting health? And I can't answer that question unless I tease those two variables apart. And for example, I will need to find some way to extract vegetable eating out of hand washing to see how much does hand washing predict health. And I'm going to use a language after controlling for eating vegetables. Or another example, say I have a hypothesis that when children are exposed to lead, that leads to lower educational attainment in life. So my hypothesis is that lead exposure leads to educational attainment. It would be a negative correlation in this example. But maybe exposure to lead also overlaps with a child's socioeconomic status. Children who are exposed to lead may live in homes that have less financial resources. They may live in more impoverished neighborhoods. So if I do a study and find that exposure to lead predicts education, I don't know, is it the lead exposure that directly predicts the education, or is it actually socioeconomic status that predicts education and just happens to overlap with lead exposure? So I need to find a way to extract socioeconomic status out of lead exposure to see if lead exposure by itself predicts education after controlling for socioeconomic status. Or as a third example, maybe I have a hypothesis that when students experience stress, that makes it more difficult to perform well in school and they get lower grades. So my hypothesis is that stress would correlate with grades. And another negative correlation, that if stress goes up, grades go down, would be my theory. But is stress the same thing or something different from depression? Theoretically, feeling stressed and feeling depressed should be two different things. But it is possible that when I assess how much people feel stressed, I'm actually assessing the same thing as how much they feel depressed. So if I do a study and I find that stress correlates with grades, I don't know, is that specifically stress that correlates with grades, or am I really just assessing depression, and depression is the thing that correlates with grades? And so to find out if stress is something distinct from depression that has its own unique effect in predicting grades, I would need to find a way to extract depression out of stress. So that's what we're talking about. In this example here, I'm going to focus on the two variables we've been using throughout this unit, which is bunny trauma and anxiety. And let's say I wanted to get a measure of someone's anxiety, and I wanted to extract bunny trauma out of anxiety. And when I use the term extraction, if I could say I want to extract bunny trauma out of anxiety, I can also use the language anxiety controlling for bunny trauma, or anxiety holding bunny trauma constant. So these are all ways of saying the same thing. If I say anxiety with bunny trauma extracted out of it, anxiety controlling for bunny trauma, anxiety holding bunny trauma constant, these are all just saying the exact same thing. We're extracting bunny trauma out of anxiety. So how would we do this? Well, what I'm going to do is actually pretty easy here. We've actually done already everything we need. Just a moment ago, we were talking about how we can use regression to predict people's scores. And we had this table where I had everyone's scores on X and everyone's scores on Y and everyone's predicted score. And then I had a final column for their errors. And what I'm going to do, I'm just going to relabel that final column. I'm not going to call this errors anymore. I'm going to change the name from error to residual scores. I'm going to call this final column residual scores. And actually, as it turns out, once we've gone through this process of using X to predict Y and getting people's predicted Y and then calculating all these errors, this column of errors right here is actually a column of people's new scores on Y with X extracted out of it. So that's all there is to it. If I want to extract one variable out of another, I simply use a regression equation, use X to predict Y, and then calculate everyone's residual scores. And those residual scores are actually people's scores on Y with the variable X extracted out of it. So here is a slide illustrating what we're doing with extraction. So to do extraction, we simply run a regression equation where we use X to predict Y. And X is going to be our perpetrator variable. It's going to be the variable that will do the extracting. Y is going to be the victim variable. It's going to be the variable that will have stuff extracted out of it. So to extract X out of Y, we simply run a regression equation where we use X to predict Y. So for example, if we want to extract bunny trauma out of anxiety, we simply run a regression equation where we use bunny trauma to predict anxiety. Bunny trauma is X, it's our predictive variable, and now we're going to label that predictive variable as a perpetrator. It's the one that's going to be doing the extraction. And Y, our outcome variable, we're going to now label that the victim variable because the Y variable is the one that will have stuff extracted out of it. And what's going to happen when we run our regression equation is that the perpetrator is going to come along and it's going to latch its teeth into the victim and suck everything it can out. It'll make maybe a kind of a giant sucking noise and try to suck everything it can out. But sometimes it might extract everything out of Y and there'll be nothing left but an empty shell. Or other times it might try to extract everything it can. It might sink its teeth in and try to suck and get everything it can out, but it might not be able to get anything out at all, and Y will just walk away totally unharmed, which is the picture I have down at the bottom, just noting that sometimes, like on the right, after things are extracted out, there might be nothing left of Y whatsoever, or other times X might extract everything it can out of Y, and Y walks away unharmed. And again, I note at the top here that when we're doing this, I'm just running a regression equation and I calculate the error for every single person in my sample. And I'm now just relabeling that error. I'm going to call it residual score. It's kind of like putting a different spin on error. Error is no longer the stuff that's the mistake we're making, but rather we're now rethinking of error. Before, if I talk about error as a mistake, how much mistake you made when you try to predict people's scores, that makes error seem kind of bad. And now we're thinking of error as that's the residual score. That's the stuff left over in Y when X is extracted out of it. That is, that's the stuff left over after X is extracted everything it can out of Y. That's what the residual score is. So when will X extract almost everything out? When will X come, if we use X to predict Y, what are the situations where X will end up extracting almost everything out of Y and there'll be nothing left? And what are the situations where X will try to extract everything it can out of Y, but Y will walk away unharmed and X will have extracted nothing out? What makes the difference between these different situations? Well, if you think about it, the key thing that determines how much X extracts out of Y is simply the correlation, the size of relationship between X and Y. So for example, let's consider what would happen if there's a perfect positive relationship between X and Y. Here's a different data set of variables, and this one is showing a situation where we have a perfect positive correlation between X and Y. So you can see everyone's score on X perfectly predicts their score on y, everyone's score just lines up perfectly on that slope. So we have a perfect positive correlation. Have at the top say r equals 1. Our correlation is 1. We have a perfect positive correlation. So if we have a perfect positive correlation and we run a regression equation where we use x to predict y, and we're going to be thinking about residual score. So x comes along, it sucks its teeth into y and tries to suck everything it can out of y. How much is going to be left over? Well, if we have a perfect positive correlation, nothing will be left over. If we have a perfect positive correlation, we use x to predict y. The residual scores, here I have the third column of residual scores, that is going to be just a column of zeros. So this column right here, that's all the stuff that's left over in y after x is extracted out of it. We used x to predict y. Here's our regression equation right here. It came out to be predicted y was, we got a intercept of 10 and a slope of 4. And if you wanted to, you could take this data set and calculate for yourself what the intercept and slope would be, or you can just take my word for it. That's our intercept and slope we get based on this data set. And so if we take everyone's score on x, multiply it by 4, add to it 10, we get their predicted scores right here. And we see for every single person, the observed score and predicted score are the same thing. Everyone got the exact same observed and predicted score. So we have a perfect positive correlation. So for every single person, observed minus predicted equals 0. So we just have a column of zeros over here. The residual score is 0 for every single person in our sample. And what that means is there's nothing left in y. We don't have variance. We don't have differences between people anymore. Everyone just now has a score of 0. There's nothing left over. Now let's look at 3 things I want to note about these results here at the bottom. So what is observed minus predicted? That's what we were just talking about. And when we have a perfect positive correlation, observed minus predicted will be 0 for every single person in our sample. So that's what we were just looking at here. It's this top equation noting that when we have a perfect positive correlation, y minus y hat will always equal 0 if there's a perfect positive correlation. What about the mean of these residual scores? I have the mean E bar, that's the mean of these errors or the mean of these residual scores. That is, if you take each score added up 0 plus 0 plus 0 plus 0 plus 0 and all the way down, divide by 9, we get 0. The average score of the errors is 0. Now this is actually doesn't matter what our correlation is here. We don't have to worry about that. This is actually will always be true, is that, and this is, if you recall, when we talked about the standard error of estimate, we talked about the step where we take each person's observed score minus their predicted score to get the residual score. And if you recall previously, I mentioned that the sum of the residual scores will always sum up to 0. And this middle equation right here is just reminding us of that fact that the mean of all these residuals will be 0, and that will simply always be true regardless of our correlation. Third, and this is going to be an important thing, what is the standard deviation of these errors, of this column right here, of this column of zeros? What is the standard deviation of those values? That is, what's the standard deviation of our residualized y? If we calculate everyone's score on y, after x has been extracted out of it, what is the standard deviation of those new scores, what I might call these new residualized scores? Well, the standard deviation of just a column of zeros is 0. There's no variance. Everybody had the exact same score, and if everyone has the exact same score, then the variance is 0 and the standard deviation is 0. And that is actually precisely what I mean by saying there is nothing left in y after extraction. So what I mean by that is that the standard deviation is 0. There's no variance. There's no differences between people. After I extract x out of y, if I have a perfect positive correlation, there's nothing left over in y, meaning there's no more variance. Everybody has the exact same score, and there's no differences between people after I extract out of x out of y. So that's what we have if we have a perfect positive correlation. Now, what if we have a zero correlation? Let's look at, here's another data set. And this situation illustrates a situation where there's absolutely no relationship between X and Y whatsoever. We have a zero correlation. So correlation equals zero. And recall that if we have a zero correlation, our regression equation simply becomes a flat line where we predict the mean of Y for everybody's score. So our regression equation simply becomes intercept plus a slope is zero because there's no relationship times X. And so that means X times that just cancels out. And our intercept is simply the mean of Y. That is, if we take everyone's score on Y and sum that up and divide by our samples, 1, 2, 3, 4, we have, I guess, 8 people. So we take those scores, sum them up, divide by 8. We'd find that the mean is actually 21.25 because if there's a zero relationship between X and Y, then our regression equation just becomes a flat line right at the mean of Y, where we predict the mean of Y for everyone's score because X doesn't tell us anything. So that's what I'm depicting here. And now let's look at those 3 equations that we looked at on the previous page. First of all, what is Y minus Y hat? What is the error or that residual score for each person? So let's look and see what happens here. If we take person number 1, that person had a score of 30 on Y, and we predicted 21.25. That's the predicted score based on a regression equation. And note that we're simply predicting the mean for everybody's score. So if you look at this column, note that we're predicting 21.25 for every single person in our sample because X doesn't relate to Y, and so we're simply predicting the mean of Y for every single person. So for this person right here, that person got an actual score of 30. We predicted 21.25. Observed minus predicted, the error is 8.75. So 8.75, that's the error, or now I'm going to call that the residual score. That's the residual score on Y with X extracted out of it. And here we get 10 minus 21.25 gives us negative 11.25. That's the second person. That's that person's error or the residual score on Y with X extracted out of it. The third person, the error or the residual score is negative 6.25. That's that person's score on Y with X extracted out of it. So what is observed minus predicted? Well, it's the same thing as observed minus the mean of Y because we're simply predicting the mean of Y for every single person. So if our correlation is 0, if there's no relationship between X and Y whatsoever, then observed minus predicted is the same thing as observed minus the mean of Y. And note, this is actually a review. We talked about this earlier in this unit about the fact that if we have a 0 correlation, Y minus Y hat is the same thing as Y minus Y bar. So this is actually reviewing something we talked about previously. Let's look at this middle equation here. Note this is the same thing as I showed you on the previous slide, and that's because the mean of the error, that is the mean of the residuals, will always be 0. Note that what we've done here, in subtracting the mean from everybody's score, that is observed minus predicted, is the same thing as Y minus Y bar, and so we're simply subtracting the mean from everybody's score. And recall that I called that process, if you subtract the mean from everybody's score, I call that centering. You're just adjusting their scores so that you have a new scale with a mean of 0. You're not really changing their scores, you're just changing where the mean of those scores are. But the shape of the distribution remains the same. So when you center scores, you don't change the shape of the distribution, you just make it so that the mean is 0. And that's all we're doing here. If we have a correlation of 0, if there's no relationship between X and Y, then observed minus predicted is the same thing as observed minus the mean. And if we're simply subtracting the mean from everybody's score, that's the same thing as centering the scores. We're simply centering the scores. So this third column right here This column of errors is simply a column of centered scores for every single person. And as always, the mean of our errors will equal 0. Now, let's look at the most important thing here. What about the standard deviation or the variance of this column of errors or these residual scores? In this case, the standard deviation of the errors will be the same as the standard deviation of y. In other words, the standard deviation of this column of numbers will be the same as the standard deviation of this column of numbers, because the distribution of those two columns is identical. There's no difference. The only difference is that the column of the residuals has been centered around 0, and the original column of y values is not centered, but the actual shape of the distribution, how far cases deviate from the mean, has not changed one bit. And so when I simply center scores, that doesn't change the size of my standard deviation. So the standard deviation of my residuals, of my error scores, is the same as the original standard deviation of the y scores. So that's why I would say that when we extract x out of y, if there's a 0 correlation, then what's going to happen is that y will walk away centered but unharmed. Nothing will happen. We haven't changed y at all. We've just simply centered y, but y is still all there, whole and intact. The standard deviation is still the same. We haven't changed the shape of the distribution or how far scores are spread out. We simply have centered them. So to review, go back up to our previous slide. When we have a perfect positive correlation, if we extract x out of y, there'll be nothing left in y after extraction. X will extract everything out of y, and there'll be nothing left. In contrast, if we have a 0 correlation, if we use x to extract y, y will be unharmed. Nothing will happen. X will try to extract everything it can, but it won't be able to extract anything out at all, and y will walk away totally unharmed. Y will be centered now, centered around 0, but otherwise y will be unharmed after extraction if you have a 0 correlation. So in sum, the key thing to note there is the extent to which x extracts stuff out of y when we use extraction depends on the size of the correlation. That is, the extent to which x extracts variance out of y when we extract x out of y. How much gets extracted depends on the size of the correlation between x and y. When we have a 0 correlation, nothing gets extracted out. When we have a perfect positive correlation, everything gets extracted out. And then when you have correlations in between, then the amount of extraction goes in between. Here is a slide just summarizing what I've been talking about. As the correlation between x and y increases, variance in the residual scores are those scores that leftover variance in y after x is extracted out of it. That's your new, so when you use x to predict y and calculate those residual scores, that residual score is your new score on y with x extracted out. And as the correlation between x and y increases, variance in those residual scores will shrink towards 0. And if you have a perfect positive correlation, then that variance becomes 0. And if you have a 0 correlation, then there's no shrinkage at all. And the variance of the residual score, that is your new score on y with x extracted out of it, is no different than what you originally started with before extraction. Now, one final thing I want to note about extraction is that when we do this process, when I use x to predict y and extract x out of y and calculate a set of residual scores for every person in my sample, and those residual scores are each person's new score on y with x extracted out of it. Now let's consider the question, what would be the correlation, say, between those residual scores, say this thing down here, maybe that represents a person's score on y with x extracted out of it. What's the correlation between the residual score and the x variable, the perpetrator, the one that did the extraction? It will always be true that that correlation will be 0. Once you extract x out of y, once you create those residual scores, once you create everybody's new score on y with x extracted out of it, the correlation between those residual scores and x will always be 0. So if I extract bunny trauma out of anxiety, and calculate everyone's anxiety score with bunny trauma extracted out, the correlation between that new anxiety score with bunny trauma extracted out, that new, I might call it your unique anxiety scale or unique anxiety score, that score on anxiety with bunny trauma extracted out, the correlation between people's unique anxiety scores and bunny trauma will always be 0. Because once you extract X out of Y and create those residual scores will always correlate exactly 0 with the original X variable, with the perpetrator, with the variable that did the extraction. And that is everything for section D of Unit 4.